So welcome to the next topic in chemistry, gases in the atmosphere. Okay, there are a small number of learning objectives for this particular topic, but quite a lot of experimental understanding. The first one is describing the composition of air. Okay, basically the top four gases that make up the air that we are breathing in every day. Understand how to determine the percentage of volume of oxygen in air. We're going to be doing that through looking at some experiments and maybe attempting one of the experiments. There's many ways we can actually determine that value. Describe the combustion of metals in the form of an example of magnesium, hydrogen, and of non-metals like sulfur. Okay, so again, we will look at the theory and hopefully do an experiment around that too. And explain why the amount of carbon dioxide is increasing and why this is important, and that could possibly link with some of you who are taking biology. And describe the formation of carbon dioxide. Okay, so here is a pie chart with the composition of air. So the majority of air is 78% nitrogen, which is an inert gas. Lucky that is too, because if you lit a match and the atmosphere was anything more than 21% oxygen, then the entire world would explode and burn in flames. Okay, oxygen, which is important for us because this is what we use for respiration and to keep us alive, is about 21%. Others are including argon, which is a noble gas, about 0.9%, and another gas which we will look at in more detail, CO2, okay, carbon dioxide. And now that's no more 0.037%, it's now more around 0.04%. Okay, so it's increasing in its composition of the air. And here is a table illustrating that point. So nitrogen is the major constituent with 78%, oxygen is next with 21%, argon is third on the line with 0.93%, and carbon dioxide is now 0.04%. I've updated that from recent values. And we have also have another range of different gases, but the four main ones that you have to know are these ones here. Okay, these ones here. So moving along, we also have to find out, well, how did we determine if that was the percentage of oxygen? How did we do that? So there are several reactions that you can do to determine the composition of oxygen in air, and we're going to look at three in particular. Those are involving copper, iron, and phosphorus. Okay, so first up, we'll use copper. So we can use the reaction between copper, which you heat, and oxygen in the atmosphere to determine the percentage of oxygen in the atmosphere. So the reaction, of course, is copper plus oxygen going to something called copper oxide. And we looked at oxides in our last unit around acids and alkalis. And there is the balanced equation. So how does it actually work? Well, what you do is you basically have two syringes combined through a tube, okay? And inside the tube you have placed some copper turnings of known weight, okay, or mass, and one of the syringes has been blocked off, and the other one you can fill with exactly 100 centimeters cubed of air, okay, about 100 milliliters, okay, because a centimeter cubed equals about, well, it is exactly a mil. Okay, so you've got 100 mils of air at the start of the reaction. You heat the copper turnings under a blue flame until the copper turnings start to turn black, because copper oxide is black in color. Okay, so you keep on heating until you see that all that wonderful copper color has gone to a black color, and then you record the amount of air that has been used up. Okay, so what's going to happen is that syringe is going to move, and you're going to record the amount of air that has been used up, and it should be around about hopefully 21 centimeters cubed, meaning that 21% of the air is going to be in the form of oxygen. Okay, that's how that experiment works. Okay, so you can also find the percentage of oxygen in air using iron. So we know from the reactivity series that iron is higher up than copper, so you do not have to heat it as we did with copper. What you can do is basically, from the diagram, you can put a measuring cylinder into water, and you bung a piece of iron at the top of the measuring cylinder, and you leave the apparatus for a couple of days. And I'm thinking we could probably do this in our science lessons. Okay, so what happens, of course, is that rust forms, iron oxide forms on the iron wool. Okay, as you can see from the diagram, and also due to the loss of oxygen, there's a pressure difference between the inside of the measuring cylinder and the outside of the measuring cylinder now. So the water kind of pushes in, and as the iron will rust, it absorbs oxygen from inside the measuring cylinder. Okay, and when there is no more change in the water level, the height of the water inside the cylinder can be measured, and from that we can deduce the volume of oxygen in air that has been used. Okay, so say that was, say, 100, that goes up to 80. Okay, so 80 there, then it's going to be using about 80 mils of oxygen. Okay, so you can also find the percentage of oxygen using the non-metal phosphorus. Okay, so what we do is you have a bell jar, you put it in some water, and coins are placed for the bell jar to rest on. Okay, and water is poured into the bell jar to a 0 level. And finally, a piece of phosphorus is placed on a watch glass floating on the water surface, okay, which you can see here corresponds to 0. Okay, then from the top, the phosphorus is lit using a hot metal rod through the bell jar. Okay, so now we'll put the bung on top. As the yellow phosphorus starts to burn, the oxygen in the air starts to obviously react with the burning phosphorus, and the bell jar fills with white fumes of phosphorus oxide. This then dissolves in the water to form a phosphoric acid solution. Okay, so because of this, the actual water begins to rise in the bell jar. Okay, because obviously there's less pressure acting on the water as the oxygen is being used up and going into the water as the form of phosphoric acid, and that means that when the reaction ends, the percentage of oxygen in the air can be calculated by the change in water level. Okay, so it's gone from 0 to about 2 or 1.18. Okay, so you can work out the difference, and that can be a measure of the percentage of oxygen in the air. Okay, combustion. So combustion is basically the reaction of an element with oxygen. And I'll give you 3 examples here, one of a metal, one of a non-metal gas, which you're very familiar with, the classic pop test, and one with a non-metal. Okay, so magnesium, which you may have done in previous years, reacts with oxygen to produce a bright white flame, leaving white ash of magnesium oxide. Okay, we'll probably demonstrate this in class, or do it in class. Hydrogen burns with oxygen to basically form an explosive reaction and form water, and we experience that in terms of the pop test. Okay, that pop is actually the explosion as hydrogen reacts with the oxygen in the atmosphere to form water. And finally, sulfur, which is illustrated in the video, will react with oxygen and form a blue flame. Okay, where sulfur and oxygen form sulfur dioxide. That sulfur dioxide actually goes on further and reacts with water in the air to form sulfuric acid. So those are the 3 examples of combustion reaction with oxygen.
Sulfuric acid. I say you don't want to see the first bit. Now, when you heat it up, the sulfur starts to melt, so it catches into the depth reactant stream. and then it sets alight. You can't see the flame very easily back there, but there's a little bit of a blue flame. And then when we put it into the oxygen, it burns much more, and it's a beautiful flame. So that's sulphur burning in oxygen, and it's a beautiful, beautiful flame. And that's going to lead us on to an acid. Everyone know what you form when you burn sulphur in oxygen? S plus O2. Try and work it out. It's like C plus O2.
Okay, so how do we form carbon dioxide? So it's formed in many ways, and this kind of links with biology. So it's formed when material burns, like fossil fuels. Okay, methane, for example, plus oxygen gives carbon dioxide and water. There's the equation, balanced equation there. Okay, so carbon dioxide can also be produced in the laboratory, and one way we can do that is by heating metal carbonates, so sodium carbonate, potassium carbonate, copper carbonate, iron carbonate, and this is called thermal decomposition. Okay, thermal because we're using heat, and decomposition because we're breaking it down, we're decomposing the carbonate. Okay, so the example which we might do as a demonstration in the laboratory is heating copper carbonate, which gives copper oxide plus copper dioxide. Okay, so copper carbonate reacts to form copper oxide and carbon dioxide when we heat it under the blue flame of the Bunsen burner. And it's an odorless gas, and also it is denser than air. Okay, that's why it's used in fire extinguishers, because it basically covers the fire and stops oxygen entering the fire and stops the combustion. Right, it's also a product of respiration. So glucose plus oxygen gives carbon dioxide and water. There's the equation, which you must be familiar with from biology. And you can also remove atmospheric carbon through photosynthesis, the opposite process to respiration. Okay, that's one way. So planting lots of trees can remove the carbon dioxide in the atmosphere and lock it in to the plants. Right, so of course carbon dioxide is important because at the moment the carbon dioxide level in the atmosphere is rising. At present it's about 0.04% and going up. And the carbon dioxide level is maintained by the carbon cycle, which we'll look at now in a little bit of detail so we have some understanding of how that's affected to global warming. Okay, so the carbon cycle, which you'll be familiar with in biology, basically says that there's carbon dioxide in the atmosphere, and it's coming from respiration, combustion of fossil fuels, okay, and respiration from decomposers, okay, and what happens is that plants die, they're eaten by animals, and this all causes carbon dioxide to be formed from respiration. And of course the fossil fuels are where what we use in cars to help power them, but the combustion again produces carbon dioxide. So because the amount of fossil fuels that is being used to power our vehicles has increased over the last 100 years, the amount of carbon dioxide in the atmosphere has also increased. And we've also cut down the number of trees, so carbon dioxide is not being used from the atmosphere to produce carbohydrates, so it stays in the atmosphere. Okay, so CO2, carbon dioxide, CH4, methane, and H2O, water, are known as greenhouse gases. Okay, so methane is caused by the decomposition of vegetation, just like carbon dioxide is, and also by the farts, basically the waste gases of digestion from animals. And it traps energy from the sun, which is striking the earth, so the earth acts, or the atmosphere starts to act as a greenhouse, locking the heat in the earth, which isn't very good. Okay, so because we want to radiate some back into space, not all, because obviously we need a certain temperature to live on Earth, but we do need some to radiate back into space. And this is called the greenhouse effect and is essential for life. So methane, carbon dioxide, and water, what they do is they're trapping the heat into the atmosphere, so it cannot be lost into space, so the temperature of the Earth rises. Okay, this is caused by an increased use of fossil fuels, increasing the amount of carbon dioxide, okay, and also large-scale deforestation, okay, meaning that the carbon dioxide cannot be taken up by the plants, So this also leads to an increased level of CO2 levels in the atmosphere. Right, so this causes the imbalance in the carbon cycle, which we've just seen, and this increased level of carbon dioxide is considered to be one reason why the global temperatures are increasing due to this increased greenhouse effect. Okay, so the next few slides, we're just going to go through some true or false questions to see if you actually have a comprehension of the causes and effects and possible solutions around the greenhouse effect. Okay, so basically 5 true or false questions. You'll be given 10 seconds to decide your answer to each question, and we'll look at the answers at the end. Okay, first question is, the hole in the ozone layer contributes to global warming. So is that true or false? Next question, recycling reduces global warming. Is that true or is that false? A record hot day is evidence of global warming. Is that true or is that false? Second to last question, global warming means less rain. Is that true or is that false? And finally, electric cars do not contribute to global warming. Is that true or is that false? Okay, so you have about 10 seconds to write down your answers, and then we're going to go through the answers and see if you are correct in your understanding of the topic. Okay, first one, the hole in the ozone layer contributes to global warming. Well, the answer is false. Okay, the reason why is that the hole in the ozone layer means there is less protection from the sun, but it does not mean that it's contributing to global warming. They're two different things. Okay, it's about UV radiation, not carbon dioxide. Okay, they do contribute the gases, but in a very small way. So recycling reduces global warming. Is that true or is that false? That is true, okay? Because recycling reduces the need to burn fuel, okay, or use electricity, so reduces the amount of carbon dioxide or greenhouse gas emissions like methane, so that's true. A record hot day is evidence of global warming. That is false. Okay, the reason why it's false is because on its own, one hot day does not provide enough evidence. There's an increased number of record temperatures, and this is evidence of a long-term pattern. Okay, second to last one, global warming means less rain. This is false. Okay, in some areas it actually means there's more water evaporating, so you actually get more rain. Okay, but however, the pattern of the rain is likely to be more erratic, so the monsoons, the time when they come, can change, and the amount of water being dropped also changes, so you get more flooding potentially. And finally, electric cars do not contribute to global warming. Is that true or is that false? That is false. Because most electric cars still have to charge their batteries and they use electricity from fossil fuel sources. And also, either make these cars which also need greenhouse gas emissions.